Hello, everybody, and welcome to the second week of CAD for Electronics. Today, we're going to be looking at circuit modification, component properties, PCB layout, data sheets, and some troubleshooting techniques. I'd like to remind everybody that there is a quiz available today. So take 10 minutes at some point and make sure that you do that to get the points and make sure that your learning is on track. Okay? The first thing that I want to talk to you about are data sheets. Data sheets are great because they're provided by the manufacturer and they are the main resource for how we find information. They tell us exactly what the criteria are for manufacturing and to use the component properly. And so they are the one resource that we're allowed to use to determine maximum voltages or power dissipation or how to even connect it properly. So whenever you reference a part, you do well to find the data sheet from the manufacturer and use that as the only real reliable resource. I say that because if I write down that a component should be capable of handling a certain current and you rely on that, you may find that certain manufacturers have different specifications. Okay, so be careful with that. The first data sheet that we want to take a look at is the 78L33. And so I will get you to go onto the internet and I want you to search specifically for the L78L33ABZ. Okay. Pause the video, go take a look at it, find the data sheet, and then we can continue on. If you scroll down to the description of the part, the first thing that you'll notice is that it does specify the packages. It specifies how it can be used. And there's a big note in here, and it says, if adequate heatsink is provided, it can deliver up to 100 milliamps. And so I want you to recall last week's work, we were going to try to put 250 milliamps through this part. And so here it says that it has short circuit protection. So it's actually going to shut down. All right. And so that's one of the reasons why we couldn't actually make that circuit work. So we're going to come back to how to make it work here in a second, but I want to draw your attention to a few other things. Notice that there are other voltages that are available. So 3.3, there's 5, 6, 12, etc. And how that works is the 78L and then the voltage. So 05 would be a 5 volt, 12 would be a 12 volt, etc. And so these are really handy little jelly bean parts that we can drop in. But know that they are a linear device, meaning the energy coming in has to equal the energy going out. There's no switching. There's nothing magical about this. And so we need to be aware of how much energy is being dissipated. And so, for example, if I was taking 10 volts at 10 milliamps and I wanted to output 5 volts at 5 milliamps, then I would have 5 volts being dropped at 10 milliamps. It gives me 50 milliwatts just simply by multiplying the two numbers. And 50 milliwatts on a package like this isn't too bad. But if I was inputting 25 volts, let's argue, and I wanted 5 volts out, now I have 20 volt drop. And if that 10 milliamps, you're into what is that? 200 milliwatts. So you now have a fair amount of power that you need to be able to dissipate. All right. So what do we do with our circuit? Well, what we want to do is we want to actually keep reading the data sheet. And so if we scroll down most of the way, you'll find a set of figures that have to do with typical applications. And in here, you will find one, it should be figure 13, that is a high current application. And this is great. The manufacturer wants to sell chips. And so they're going to give us all sorts of ideas of alternate uses for their IC as well as make sure that we know how to install this chip properly and how to put the capacitors around it. Note that I actually got it wrong last week, that the 0.33 and the zero point 0.1 microfarad are inverted here. So we'll change that this week. But we'll also take a look at how to get more current out of this device. And so there is a 7833, so you lose the L, and it's a much bigger package. And it's capable of delivering up to an amp and a half if properly cooled. But it's more expensive and doesn't allow us a couple talking points. And so this is definitely an option for us. As you can imagine, a transistor can be fairly inexpensive, and they can definitely dissipate a lot of heat. You could get a huge TO2 case on here, as opposed to the TO220, which a 7800 series would be. And so the way this works is the bulk of the current passes through Q1 here, IQ1, and therefore never really heats this little part up. So does that mean that you get a freebie? No, the heat dissipation still needs to happen here. This is still a linear device. So if we're drawing a full amp, then whatever voltage drop times that amp needs to be dissipated across these two devices. Technically these three devices. But you'll find that the bulk of it, and we could calculate the exact current going through Q1. We're not going to bother today, but we could then design the circuit exactly to suit our thermal needs. Okay, so let's take this circuit and we're going to apply it to our circuit from last week. And so what I want to do is, using the recommendation from the manufacturer, we're going to add the PNP transistor. We're going to add a resistor, and we're going to make sure that it is connected properly. We're also going to make sure that we did use the the 4148W diode, because they're capable of delivering more power. And we're going to bring up that capacitor from our previous value to 680 microfarads. And while we're at it, I'll take a couple minutes and show you a couple things that you would have had when you were trying to get your circuit going. Okay, so here's my circuit from last week, and like I said, this seems to be backwards. So what we'll do is, and I apologize, I should have caught that myself, but things happen, right? This is why we read data sheets. So, okay, I'll take this, flop them around. And you can see that modifying the circuit really isn't, it's not that difficult. Maybe this is a good opportunity to talk to you about one other thing. So when we connect these bypass capacitors, one of the things that we want to make sure that we do is that we connect them as close to this device as possible. And there is a technique to this. And the technique is to basically show that these are as close as possible. And so what I've done here is I've turned off the wire auto router, which doesn't mean what you're maybe thinking it does, but will allow us to, instead of making these nice 90-degree bends, to put in an angled bend. Okay. And so what this does is it tells us that this is a star point. These grounds are as close as I can possibly make them. All right. So that's a great little technique. Okay. And so here we are. I've changed this out to a 3 ohm resistor, and it should be 3.3, but it doesn't really matter. When we try to run this, you'll notice that I don't get to my 250 milliamps, and my voltage has dropped substantially. And so what's going on here? Let me throw in an oscilloscope here super quick, and we'll just take a look at what's going on with that point. And we're going to spend some more time talking about the oscilloscope later, but here we go. And so I'm going to flip you over to DC. I'm going to double click on the radio button. And as you can see, we definitely have a messed up, um, sorry, we definitely have a signal that's not what we expected. Okay. It's deformed and it's nowhere near a DC signal. And the other thing is that it all seems to be well below zero. And so there's a few things going on that we need to talk about. One is there is no ground reference here. So the oscilloscope doesn't know where 0 volts is in our circuit. And so the first thing I'm going to do is I'm going to go into my terminals and I'm going to put in a ground. Okay. And now when we run it, we get a different looking signal, but it's still, well, it's what's really kind of happening. So why don't we turn this up? So we can see that there is a voltage, but it is extremely small. Okay. And even if I slow it down, basically everything's in shutdown. Okay. So let's grab our calculator, and we should be able to provide 50 milliamps to this without much problem. So if I have 3.3 volts divided by 0.05 amps, means that this should be about 66 ohms. Give me my 50 milliamps. And there we go, 66. And now when we run it, we can see that we are getting our 50 milliamps, and we have our 3.3 volts, and it's nice and clean. So that's good. That's this circuit would be sufficient for that. If, however, we take this up a little bit higher, so instead of 50 milliamps, let's get some more. So that'll be 132. So this should provide our 100 milliamps. When we go to run it, we can see that, again, it's reasonable, and we don't have any real issue at the specified voltage with 120 milliamps. As we move up further, let's take this up to, we're going to go down to, so half this give us double the current. And so here we are. We're now running at, notice we are already having an issue. Our voltage is dropping. Our current isn't quite where it needs to be. And we're seeing some chop here on our DC signal. So we're not able to provide sufficient current at 100 milliamps. And so this is a problem even before we get to 250. So let's stop our simulation. We'll get rid of this, and we can start to bring in our other components. Okay, so let's go ahead, and we're going to pick a couple parts out. We need to go to our component selector here. We're going to pick, and we want our BD140. So BD140. And sure enough, it's a NP transistor. And we also need, so the capacitor and the resistor, we already have those packages, so we can go ahead and say, okay. And let's start by placing our component. Now, note where the collector and the emitter are. Okay, so if we look back to our manufacturer's recommendation, they give us a big tip. We don't even really need to think about this too much, but let's grab it anyway. So here we go. Notice where the collector and emitter are. So we're basically traveling along this way. We think of it as voltage flow, and we will connect this up like so. All right, so. And we need to add a resistor. So let's grab this guy and we're going to move it down a little bit to give us some more room. We'll grab our resistor. And so let's see. First trick of the day. I don't want to cut this. I'm going to be pragmatic. I'm going to hover over this line, okay? Like so. And I'll click. And notice that it notice that it's in the wrong place is the first thing. So Control Z, I'm going to get rid of that. I'm going to move this capacitor back so that we actually put this in the right place. I'm going to get rid of this because I don't need it. And we're going to try that again. And so I'm going to take my resistor, I'm going to place it in here, and I will select it. I can now connect the base, and we can tighten things up, keep our space as neat as possible. And we want to change this. Let's just go with their recommendation. So 30 ohms. We'll leave that for now. And so we have our current coming through, right through here, across, and out the back. And so far, so good. Okay. One of the things that you're going to find is that a 30 ohm resistor is actually hard to find. There are standard values. They're called the E series, and I will create a video for that at some point for you to take a look at. But you'll find that a 33 ohm is a much more popular resistor. So let's change that to 33 ohm. And I want to change this bulk capacitor this time to 680 microfarads. And that's going to help make sure that we have a filtered DC coming in. And so as you learn in electricity, this bulk capacitor fills in the valleys of the rectified DC. And as long as that's kept up, then we're good. This 10 microfarad over here is only going to deal with the transient loads created by our circuit. And so today we don't really have much, so we're just not going to worry about it. All right. Now, one of the things that we can do is we can drop in a meter here, and we can watch how much current goes through here. But I want to take a second and show you another tool. The reason why I want to show you this tool is the ammeter causes a bunch of problems when it comes to layout. And so avoiding it is maybe better. And so what we're going to do is we're going to go here to probe mode, and I want to click on current. And I'm going to place a current probe with the arrow pointed in the voltage flow. So what direction from positive to negative, the little arrow showing. Okay. And we can also measure the voltage. So let's grab a voltage here, and we'll measure the voltage here and here. And while we're at it, we'll change this so that we can get our full 100 milliamps. That's great. And let's let it run. And so here we can see that we have our 9 volts RMS here, which is a little bit low. We have less than our 100 milliamps coming through here. We have 3.3 volts here, but it is picking up our 100 milliamps through the load resistor. So where's the extra current coming from? The answer is here. This is sourcing, we'll call it 10 milliamps through the regulator, which is fantastic. The circuit is now working exactly the way we want it. So we'll pause this. We'll go back to our part selection, and there's a couple more components that we want to lay in at this time. Last week we loaded these SIL connectors, and so let's toss them in. There we go. And notice that they do label them J1 and J2 as we lay them in. There's nothing specific so far about that, so we won't worry too awfully much about it. But we do want to be careful here. And the reason is that, remember, I said these cause a problem. You want to make sure that where you connect it, it's upstream, if you would, of this. Okay, so here we go. I'm going to connect this like so. The reason is if I connect it here, when we go to do our PCB layout, it doesn't know what to deal with this. It will actually exclude it, and this wire would not get connected. So the right place to put it is upstream of this. And remember that this is basically just for our simulation. All of this will be excluded in the PCB layout. Okay, this is fantastic. So this is the first portion of our assignment. I'm happy with this. Let's get ready to print this, and so I'm going to ask for a couple things. One is for some of this stuff, I'm going to want a PDF, and some of it I'm going to want the PSPRJ file, which is it's a zip file that has all of the design for Proteus in it. So if I ask for the PSPRJ file, it's actually the Proteus file. And the other way that I'll ask for information is through a PDF. And so the PDF is great because I'm going to, it's also how we would send it to the printer. Okay, so let's go through that. So I'm going to go into File, Output, Print Design, and there's a little pop-up menu here, but what we really need to look at is a few things. One, you want to print in landscape, you want to fit to page, and if you're sending it to me, it's nice if you send it in color. If you're sending it to your printer, that's fine, you don't have to. But the next thing is that we're going to have to select the printer. And if you're looking for a PDF, the Microsoft print to PDF is great. If you have a different system, you may need to install something, but the idea is that you will print to PDF as opposed to doing a screen capture. And what it means is a much cleaner, neater printout. Here we are. I'll pop mine on the desktop. I'll give it some logical name, and that's it. You're pretty much good to go. And here we go. This is what you should end up with. A very clean and neat printout. Notice, however, that the author isn't in here and it has a bunch of other stuff that didn't get filled in properly. Let's take 1 second and I'll show you how to put your name on this. So the way to do that is I want you to go under Design, Edit Design Properties, and under Author, put your name. And this is a great way to deal with this, and you're done. That's it. It's that easy. Later we'll talk about how to remove the path and clean up the file name, and we'll make it all pretty. But for right now, I would ask that anything that you send me does have your name on it. All right. Okay, the next thing that I want to talk to you about, and I realize this is slightly out of series with the slides, but that's okay. We'll come back to printing the PDF, printing the PCB layout in a moment, possibly after we have a PCB layout. But we need to go in and change a few parts. And the easiest way, and we looked at this last week, easiest way to change some of these parts is to actually just go into the property editor here and or edit component menu, and we can start to change things. For example, the LED does not have a PCB footprint associated with it. And there's a couple ways that we can deal with this. One is if there's a little pull down here, you could select a package that's already associated with it. The other way is we can go hunt for it. So in this case, we know that this wants to be an LED, and there is actually a footprint called LED. So we'll select that, and that should be good. And what else do we need? We need to change a bunch of parts. The one thing that we need to be really careful of, however, is that we do not change the Lisa file. Okay, so this is the model for the simulator. Okay, and as you can see, it doesn't really allow us to change this, but you do need to be careful. The other thing is that you can change some values and it will have a negative effect. So, for example, some of these, I see that they've blocked it now, but you used to be able to change the voltage of this, and you could really mess things up a lot. The other thing to be careful of is that if you change something like the part number in this to a 78 L05, it's going to do a couple things. One, the footprint's not going to be right. Two, the voltage is still going to be 3.3 volts. So you definitely don't want to do that. Okay? So be cautious what you change. What we can change, however, is the value of the capacitors and the resistors. When we change those values, they actually do change in the simulation. Okay. And so what we want to do is we want to change these values. Okay. So we want to change our 680 microfarad capacitor to elec rad 30. We want to change the 100 microfarad capacitor to rad 20. Okay. The 100 nanofarad to cap 10. The same with the 330 nanofarad. The 33 and the 330 microfarad capacitor or resistor, notice they are different. So I want a res 50 for the current shunt resistor and a res 40 for the LED resistor. We want to make sure that the diodes for the 4148s are set to diode 25. And finally, the BD140, instead of a TO220 case, we're going to set it to a TO126. So let's go in and change this one, TO126. That's good. And I believe it does come in the other package. No, okay. Good enough. There we go. So that was diode. I'll do it. Diode 25. There we go. And this is basically going to make sure that we have a smaller footprint. Okay. And of course, you'll have to do it for all of them. Rather than doing it this way, what I'm going to do is I'm going to go back here and show you a shortcut because I love shortcuts. I'm going to copy and paste. Okay. Just save some time. Okay. So that should be it. Everything should be set. And here we go. Let's go to our PCB layout now. So the first thing that we can do is if you're not in Imperial, you can always select over so that we're in Imperial. Under View, you will find there are a bunch of snaps for the grid. Okay, and so if I zoom in here, you can see it a little bit better as I switch between them. So F4, you'll notice, is 50 thousandths, F2, F3, F control F1, right? We'll take it down to a crazy 1,000 snap, but here we go. So you can see it gets much narrower. I'm going to leave mine nice and big for now. And the first thing that we're going to do is we're going to create a board edge. Okay, and it's really important that we follow this exactly. I don't know how many times I've had students not select the right layer for their board edge. Okay, so let's go through this. We're going to pick a 2D box mode. And we're going to go down. We're going to change it from top silk. We're going to change the board edge. And I'm going to follow along here from 0, 0. I'm going to make it 40 by 50 millimeters. So let's change this back to metric. Okay. 40 millimeters. And if you look down at the bottom, you can see 37.5, 40 by 50 millimeters. So up 40 and zoom out. There we go. I'm just going to click on here. It's wrong. Okay, so what to do? Redraw it? No. I'm going to go to my selection mode, and I'm going to double click on it. So that's double left click, not double right click, because that'll erase it. And you'll notice that we can actually type in our width and our height. So in this case, I want 40 millimeters tall, wide, and 50 millimeters tall. Good, done, finished. It's much easier than trying to mess around down here with our little values. Just type it in, okay? The next thing is that we want to go over and select component mode. Do not pick the package. You'll notice that we could actually draw a bunch of packages on here, but it's not trying to connect any of them. If you see this, you're definitely in the wrong mode. And so make sure that you use the component mode as opposed to the package mode. All right. One of the tricks that I like to use when I start to do layouts is to actually have my schematic and my PCB layout available to me. And so what I'm going to do is I'm going to take my my window out of full screen like this, and I'm going to grab the schematic in this case, and I'm just going to drag it off. And what that'll allow me to do is to have my schematic open as well as my PCB. And so this is a great way for us to basically follow the logic through as we're placing our components. And why is that important? It's really important for us to lay our components in a logical fashion so that traces do not have to run around all over some circuitous route in order to join everything. And so I'm going to go through this, and you can follow along if you wish. You can also do this as you want. But let's start placing parts. And so you'll see the first component here for my power is J1. So I'm going to grab J1 and I'm going to place it. Now I like personally, and this is completely up to you, I like to have the bar here on my plug facing in. But that's okay. All right, so the next thing that we get to is D1 through 4. And so let's grab our diodes, and I'm going to place them in a logical fashion. And now this would make more sense for me to be in imperial because these are imperial parts. Okay? So I'm going to place D1, D2, D3 wants to get turned around and wants to get connected there with that. And D4, oops, here. And it's not quite right, so we can grab things and move them around. Notice where you grab the part makes a difference though, right? So if I grab it here on the terminal, it will actually move it on the terminal. We can also move the labels, okay, so that we can make this look neater. Okay. Now, the next thing that I get to is this capacitor. So I'm going to put in the capacitor. That's a 680 microfarad, and you'll see that it's quite large. Okay, so let's place it somewhere logical as well. And so now I want to talk to you for a second on traces. Notice that everything's kind of flowing in a logical pattern. You don't have to wait till you're finished to start laying the traces, but you can place them as you go. It means that you may have to delete things later, but it's okay. When we do lay our traces, you have the option of using top or bottom copper, and you can choose it down here, or the page up and page down allows you to switch between them, or if you have internal layers. Okay, so I ask that I want you to manually lay out these traces, and I want you to do it only in bottom copper. And so I'm going to do this portion, but not the rest of it. I want you to do it. Okay. And so when we lay out a trace, it it we want to start with one of the terminals, and so you have to select a terminal, and for the beginning and the end. Okay, and then you can do the next one, and the next one. This design is fairly simple, so you should be able to lay this out in such a way that you do not need to use top copper at all. This is relatively simple. Okay, one thing that I mentioned earlier, and just to reiterate, is that if you did put in a current meter somewhere that is in the current path, putting a short around it will cause a problem when you go to simulate it. Not putting a shunt around it when you go to do the PCB layout will cause a problem. Basically, this will be an open circuit, so make sure you deal with that. And so this is here's the layout. Here's what I want you to make with the proper diodes. Those are not the proper diodes, but you can see that I was able to actually lay everything out just fine. So I want you to do the same. It's completely up to you how you connect it, but do that. And so for next week, I want your working layout. So I want your PDS PRJ file. This way I can make sure that it actually does simulate for you. And I would like the PCB layout done with the correct footprints and dimensions. Okay. Now, perhaps I should show you how to dimension a block here. By dimensions, I didn't mean that you need to dimension this, but it's a good aside. By dimensions, I meant that I want the correct size right size PCB. But let's talk about dimensions for a second. If you select this tool here, this is your dimension tool, and let's put our dimension on, say, mechanical 4. No, because that's yellow. Let's put it on mechanical 3, and we select. Let's go back to metric here so that everything lines up. And I select like so. You can see that we can actually put dimensions on our board. It's not necessary. It's not really required, but it's a neat tool to have available to you. All right. I guess the last thing that we need to talk about is how to output this. If I ever ask you to give me a PDF of it, the idea here is, let me just put this back in here. The idea here is that we want to go to output instead of a file. We want to go to print layout, and you can see that we have our layout, and you can zoom in if you wish. Okay, and instead of monochrome, if we say white paper, what it will do is it will allow us to print literally in color. And the other thing is that instead of printing, okay, a couple of things, I guess. If we print to separate pages, it means that when we print this to our PDF, okay, so we're printing to PDF, and I'll say okay. I'll give it some logical name. You'll notice that each page of this is actually a layer. So here's my top copper, my silk screen, my bottom copper, my top copper, and the board edge is shown on each of the parts. This is a great way and makes it super easy for me to look at your PDF print, and it would be appreciated if you did follow this for any PDF prints of your PCB. All right. Okay. So as always, thank you for watching. I hope these videos are helpful to you. If you have any questions or comments, suggestions, please email me. Let me know. And if you start to fall behind, I want to hear from you as soon as possible. And of course, if there's any confusion or any extra information that you'd like, I'm always willing to create an extra video to help not just you, but the rest of the class. All right. So have yourself a good week, good luck, and hopefully you're enjoying this. All right. Bye now.